Okay. Okay, so my question is, why is sine of theta approximately equal to theta a good linear approximation for the sine of theta? Because
sine of theta, I don't know.
It says it is.
Ray doesn't know, but I trust it.
because you trust it?
I don't think it is.
You don't think it is?
Wait, no, I don't.
Well, it's just small enough.
Yeah, it works for really small numbers, right?
It's close to
gonna,
zero.
yeah, close to zero, you're going to be okay. Because if you look at the graph of the sine of theta, if you are starting here down.
Wouldn't it work until 1?
Well, it depends on how
We're
close
gonna
you
do
want to be. But why is not the graph of the sine of theta? If you think of the graph of the sine of theta, that right around 0 in this little range here, it's really close to 0 coordinates. Okay, so that's why they're able to do that.
So it
All right?
doesn't work all the time.
No, not at all. Otherwise, we wouldn't use the sine function at all. We just say, right around the origin, it's real close to 0. Okay. Another example occurs in the theory of optics, where light rays that arrive at shallow angles relative to the optical axis are called paraxial rays. In paraxial or Gaussian optics, both sine theta and cosine theta are replaced by their linearizations. So they use this, and then they use cosine theta is approximately equal to 1, because again, if you think about the graph of the cosine function, it looks like this. Here's 1, right? So in a range real close to 0, cosine is very close to 1. Okay, so they do use it sometimes. The results of calculations made with these approximations became the basic theoretical tool used to design lenses. So the next time you put on your glasses, thank goodness for linear approximation, or I would not be able to see. Okay, so this is the math part that we're going to get back into here. The ideas behind linear approximations are sometimes formulated in the terminology and notation of differentials. And so we have been working with derivatives, right? So we have said that dy dx is equal to the derivative of f of x. When we're going to change this and talk about differentials, we're just taking this and solving it for dy, which is very simple. How do you do that? You multiply by dx, so that the differential is just looking at the change in the y. Dy becomes the dependent variable, and it depends on the value of x and dx. Okay? And so let me show you graphically, visually what we are talking about here. Here is the original function right there. Okay? If we're looking at the average rate of change, bless you, of this function over the interval from x to r, then you would take the change in y, right, that the function had, divided by the change in x. That would give you the average rate of change. Okay? If we want to do the derivative instead, notice that again for values very close to the point P, dy is close to the change in y. All right? And that's a much easier thing to do than to do the average rate of change. So let me show you an example of what the heck I am talking about. Okay? So we're going to compare the values of the change in y with the value of dy in two different cases. One is when x changes from 2 to 2.05, and then another one is when x changes from 2 to 2.01. In which of those instances, A or B, do you think that the delta y and the dy will be closer to each other?
2.01.
Right, from 2 to 2.01, because the delta x is smaller in that case, and so the error is going to be smaller as well. Okay? All right, so first let's figure out the delta y. So to do that, I would do what? What? That's going to be to give me the dy. Okay, I need to plug x into here to get my first y, and then I need to plug x into here to get my second y, and then subtract those to see how much the y has changed. So f of 2 is 8 plus 4 minus 4 plus 1, which is 9. And then calculator me please, somebody. F of 2.05 is going to be 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1, which would be what? 9.717. Okay. So that means in this case the delta y is how much? 0.717. Okay. The e, what? Ooh, good question. Yeah, because we're going y2 minus y1. Okay. Okay. In the dy thing, here's how you do it. You start by taking the derivative, and you get 3x squared plus 2x minus 2. Okay, so my dy is going to be that derivative times the change in x. Okay? So, what am I going to plug in here for x to figure out what dy is? No, 0.05 is the change in x. No, because we don't know anything about this with the 2. Yes, so we're going to take the original x value and plug it in here, and then multiply it by the change in x. So I'm going to go 3 times 2 squared plus 2 times 2 minus 2 times the change in x. So if x changed from 2 to 2.05, the change is 0.05. So this is 4 times 3 is 12, plus 4 is 16, minus 2 is 14. What's 14 times 0.05? What's 14 times 0.05? Come on, it's an easy one. 0.7. And so when we did, thanks, they have a nice job. So when we did the change in y this way, which took a lot of steps, because you have to plug in the x1, you have to plug in the x2, and then you have to subtract them. We got 0.717, that's the exact answer. When we did it with the derivative, which is a little bit easier, you just take the derivative and then plug in 2 and plug in the change in the x. We got 0.7, which is pretty close to the answer we were expecting.
So
Right?
basically, it's just another way to do it.
Yes, awesome. Okay, so let's play again with these things over here. So we already know what f of 2 is. That is 9. Now, since I'm out of room, Gabby's going to just type 2.01 in on her calculator and tell me what you get when you put 2.01 into the original equation.
So dy equals f times x times dy.
Yes.
Oh.
Somebody's got
Oh.
Sorry.
The world is waiting.
Are you waiting? I'll do it.
So Gabby's got it.
Yeah,
What'd you get? Somebody's got it.
that was wrong.
Okay, so this is going to give us 9.1407. Okay, so that is a change in y of 0.1407, right? Okay, so now if we try to estimate that same thing using differentials, we already know the derivative. So you take this derivative and you plug in 2 again, which got us 14, okay, times what's the change in x this time? 0.01, and so that comes out to be 0.14, which is very close to 0.1407. Okay, so differentials are a little faster and easier than calculating the actual change in y. Okay, but it only works if you are looking at two values that are very close to each other. If you wanted to figure out the change between 2 and 5, for example, this is going to be a bad deal.
So this
Okay,
what's the part?
you're going to have a bad time. I really have no idea, Evan. It's Friday. I'm really tired. I'm just rolling.
Oh my gosh, me too.
Okay. Okay, and then this is a bunch of blah, 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 blah that shows how this is related to what we did in the very beginning. And if we apply this same thing to the linear approximation, we'll come up with the same formula that we did for the linear approximation for that, okay? All right, let's try one more here, a little word problem. The radius of a sphere was measured to be and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? Okay? So we know that the equation for the volume of a sphere is
4 pi r squared.
4/3 pi r cubed. Very good. 4 pi r squared is the surface area of the sphere. Okay, you know you're going to need a cubed if you're talking about volume. Okay? All right, so if we take the derivative of this,
4 pi
dVdr, if I put the 3 in front, is 4 pi r squared. Isn't that weird that the volume of a sphere changes at the same rate as the surface area of the sphere?
Makes sense, actually.
Okay, so if I want to solve this for dV, then I have to just multiply both sides times dr, and I get that dV equals pi r squared dr. Okay? It's not complicated at all. It sounds complicated, but it's really not. Hold on a second, Mary. Let me just go because we're almost done. And then we're going to have question time. All right. What numbers am I plugging in here? What's the radius? 21. What other number am I plugging in here? 0.05 because I want an error, a change in the radius of at most 0.05. Okay? So if I plug those in there, dV equals 4 pi times 21 squared times 0.05. So we kind of do some calculations in my head. Comes out to be approximately 277. Okay?
I don't actually.
So that means that if you are creating a sphere and you know that the machine that you're using to make the sphere is going to be with the radius of the sphere somehow is what the machine's making. I don't really know how that would make sense, but anyway, you know it's going to be accurate within 0.05 centimeters. If you're wanting your radius to be 21 centimeters, your error in the volume of your final product could be off by as much as 277 cubic centimeters. Okay, it does sound like a lot. Yeah. Yes. Get a better machine.
What if instead of making it bigger, what if it was smaller by that percent error?
It could go plus or minus.
Yeah, so you plus or
I
minus.
know it said maximum, so that's good.
Right.
Okay, well, the original
Mary?
value might
What?
have been 38,792.
Oh,
So I guess
I
that's
see.
really not that big.
Okay, say that again. 38,000 what?
792.
Okay, so if you made it exactly correct with a
Yeah.
21 centimeter radius, yeah, you'd come out to be this. So yeah, I guess that's not really that much of a kind of percentage. Okay, what's that?
Like you're like the Sputnik, like.
Yeah, well, those all have tolerances that they need, right? I mean, that same thing happened with our.
That's what it did.
So, hold on a sec. That's all I've got. This concludes chapter 3. Far and away the most exciting chapter of calculus in the entire book.
It's only
How long did we spend on this chapter?
A month.
2 months? A month?
A month.
Okay. Month and a half? All right. Tons and tons
I
and
thought
tons
it
and
was
tons.
goes into like.
You said, yeah,
No.
you did. You said
I said derivatives will take us to Christmas. Chapter 4 is more on derivatives. Okay, so we have more to go. In fact, we're going to wrap around into January still on derivatives.
Are you
Okay.
ahead of last year then?
I don't know. The big question is, how much time are you spending outside of class?